Hey, this lecture is on section 5.1 out of the textbook on eigenvectors and eigenvalues. So, we've been playing with matrix multiplication, matrix vector multiplication. Let's take a look at something that happens sometimes. So, consider this matrix A that we give here. And let's plot the vectors v and the vector A times v. So after we do the multiplication for a selection of vectors. So for example, if our vector is 1, 0, we multiply it out. What do we get? We get negative 5, 8. So 1, 0 for v. After we multiply it, we get this vector AV. Do it again with some other examples. 1, 1. So we have the vector 1, 1 right there. Multiply it out. What do you get? You get negative 9, 15. So you get this big vector up here. Negative 2, 1. So you start out with a vector here. Multiply it out. You get 6, negative 9. A vector down here. So this is just matrix vector multiplication. We're transforming one vector into another vector through the multiplication process. But now look at this vector. 1, negative 2. Something a little special happens here. When we take 1, negative 2 and multiply it out, we get the vector 3, negative 6. That's on the exact same line as what we started out with. So we take our vector, and when we do this matrix multiplication, what we get is just a scalar multiplication. It's the same thing as taking the vector we started with and multiplying it by 3. This is a very special case. It's something very special that happens with matrices. It has all kinds of practical applications, but when this happens, when multiplying a vector by a matrix gives you just a multiple of what you started with, we say that that vector that we started with is an eigenvector of the matrix. The number 3, so the scalar that it's multiplied by, is an eigenvalue. So A times V is equal to 3 times V. That is, when we have that, we call that an eigenvector and an eigenvalue. So for a definition, let A be an n by n matrix. A non-zero vector, note non-zero vector, V in Rn, is called an eigenvector if AV equals lambda V for some scalar lambda. And that scalar is called the eigenvalue of A that corresponds to V, to that vector. So for example, we have this matrix, and if we multiply it by negative 1, 2, 1, what do we get? Well, negative 1, 2, 1, for the first row, we get negative 4 plus 12 minus 5. The second element, we get negative 9 plus 14 minus 22. The third element, we get negative 8 plus 16 minus 11, and then when we add these all up, we get 3, negative 6, and negative 3. That is just a multiple of that. So our matrix A times negative 1, 2, plus 1 is equal to 3, negative 6, negative 3, which is equal to 3 times what we started with. So we say that an eigenvector of A is negative 1, 2, 1, and the eigenvalue of A corresponding to that vector, to negative 1, 2, 1, is 3, negative 3, is negative 2. Okay, so that's an example of another eigenvector and eigenvalue. So we're going to look at how to calculate these. And as I mentioned, eigenvectors and eigenvalues have lots of applications in real-world problems. They kind of show where things are corresponding, where things align, where things multiply, where you get certain nodes of things. It actually, in physical and chemical modeling, one of the first things you're going to often do is you're going to look for eigenvalues and eigenvectors. You do it a lot in economics, in all kinds of applications. So, as an example, here we have a matrix that has 2 eigenvalues. We're going to see how to find their corresponding eigenvectors. So I'm giving you the eigenvalues. Let's find the corresponding eigenvalues. So the first one, lambda 1 equals negative 1. So with our matrix, what does this mean? This means that A times some vector V is equal to negative 1 times V, and we're looking for V. So 1, 6, 1, 2 times V is equal to negative V. Rewrite this a little bit. 1, 6, 1, 2 times V. Bring that to the other side. Plus V equals 0. Rewrite it just a little bit again. 1, 6, 1, 2 times V plus, I'm going to multiply this. I'm going to stick the identity matrix in here times V, which we're allowed to do because the identity matrix times a vector is just equal to a vector. So that vector equals 0. Now, we know when we have this, we can combine things. So 1, 6, 1, 2 plus 1, 0, 0, 1 times V equals 0. One of our properties of matrix multiplication and addition is that we can combine things this way. So add together those 2 matrices, we get 2, 1, 6, 3 times V is equal to 0. So after this type of calculation, what we're doing is we're looking for the matrix V, or the vector V, that multiplied by that matrix gives us 0. Hopefully this is starting to look a little bit familiar. So how do we get this? Well, we want our matrix equal to 0. We use our augmented matrix to look for solutions. So 3 times row 1 minus row 3 is the new row 3. We get 2, 1, 0, 0, 0, 0 very quickly. And I'll just reuse this to do 1/2. Oh, sorry. 1, 1/2, 0, 0, 0, 0. And now we look for solutions, or we pull out our solutions from here. So what do we have? We have x1 plus 1/2 x2 equals 0, and x2 equals x2. That's our free variable. Rewrite just a little bit. We get that x1 equals negative 1/2 x2, and x2 equals x2. x2 is our free variable. So what do we have now? X, which is x1 and x2. Oh, sorry, I call it v. So v equals x1 and x2. This is equal to x2 times negative 1/2 and 1 when we write it out in vector form or in general form. So this gives us our eigenvector. Notice that any vector that satisfies this is our eigenvector. So an eigenvector is equal to the set of all x2 times negative 1/2 1, where x2 is scalar. So any vector that satisfies that will satisfy this equation. That's for our first one. So this was for lambda 1 equals negative 1. But I said we have a second one. We have lambda 2 equals 4, and I'll leave this as an exercise. So try it out. Do the same thing. Follow through in the same way. AV equals 4 times V. Manipulate it around so you get this sum matrix times V equals 0, and then solve it out and see what you get. And that gives you your eigenvector. So you see, if you have an eigenvalue, you can get the eigenvector. And this whole process should look familiar. This is finding a null space, which we did the last few classes. Eigenvectors are really null spaces of a certain matrix. And we'll see that a little bit more in a few minutes. So, finding eigenvalues and eigenvectors. So far, I told you, or we just saw in the last exercise, if you have the eigenvector, the eigenvalue, how do you find the eigenvector? And we saw how to solve that. But what if you don't have either? What if you don't have the eigenvalue? How do you find that? Well, here we're going to reach back into some of the properties we've seen about matrices, and we'll see how we can find the eigenvalue. First off, let's manipulate this a little bit. When we're finding eigenvalues and eigenvectors, what we're doing is we're solving this equation, but we're looking for both the lambda and the x. So we're looking for two different values when you don't have your eigenvalue. First thing we're going to do is we are going to find those eigenvalues. And you'll find when you do this, normally there's multiple solutions for it. Sometimes there's only one, but usually you're going to find multiple eigenvalues for a given vector. So let's manipulate this a little bit. We're looking for, a solution to ax equals lambda x. Well, this is essentially what we did in the last one. Our lambda, we can stick the identity in there, because the identity times your vector is equal to your vector. Now bring that over to the left-hand side, and you get ax minus lambda in equals x, of x equals 0. And then just gather together your terms, and you get this equation. A minus lambda times in equals x. So, that's just a matrix times a vector equals 0. But what we're doing here is we're looking for this lambda. We don't know what this lambda is yet. But how can we find that? Well, for here, we're now going to use some of our properties of matrices. So we have a matrix times a vector equals 0. And the key is that this vector, remember, cannot be 0. So we're looking for a matrix that has a non-empty null space. Or a null space that's more than just the 0 vector, I should say. So we are looking for something that has an infinitely sized vector space, null space. So to find eigenvalues and eigenvectors, we have to solve that equation. And just remember that we say that x equals 0 is not an eigenvector, so we're looking for a non-zero value that satisfies that equation. Remember one of our properties. If we have one vector that satisfies it, any multiple of that vector satisfies it. So that means there's infinitely many solutions. So that product has to have infinitely many solutions. What does that mean? Well, here's where we're going back to our properties of matrix multiplication, linear independence, invertibility, all of those properties we saw before. If this has an infinite number of solutions, then the matrix, right here, that matrix has to be non-invertible. If the matrix is invertible, remember, that means we have an onto relationship. That means that there is no non-zero solution to that equation. So we are looking for a matrix that is not invertible. Now, how can we tell if a matrix is non-invertible? Here we look at the determinant. Remember, a matrix is not invertible, a square matrix is not invertible if and only if its determinant is equal to 0. So, the conclusion of all this is that we are looking for a lambda where the determinant of A minus I lambda is equal to 0. And we can use this to find all of the eigenvalues for our matrix. It all comes down to finding determinants and finding a lambda where that determinant equals 0. This is pulling in a lot of ideas from our previous classes and previous chapters. But this is the core idea of finding eigenvalues. So here's an example. Find the eigenvalues and eigenvectors of this matrix. First step is we find the eigenvalues. So we have to solve, using what we had before, for the determinant of A minus lambda I equals 0. And we know how to find a determinant. So what is this? Determinant of A 1, 0, 0, negative 1, 2, 0, 0, negative 1, negative 1, minus lambda I is lambda 0, 0, 0, lambda 0, 0, 0, lambda. That's our determinant. We want that to be equal to 0. So combine those two matrices. So the determinant of 1 minus lambda, 0, 0, negative 1, 2 minus lambda, 0, and 0, negative 1, 0, negative 1, and negative 1 minus lambda has to equal 0. So we're looking for the determinant of this matrix with some variables in there, with our lambda in there. But now note that this matrix, this is an easy one to solve because it is upper triangular. And we saw that when it's upper triangular, we can very easily get the determinant by multiplying all of the diagonal entries. So the determinant of this matrix is equal to 1 minus lambda times 2 minus lambda times negative 1 minus lambda, and that equals 0. So we now have an equation for our matrix by using the for our eigenvalues by using the determinant. It's just all of the possible lambdas where this equals 0. So our eigenvectors, our eigenvalues, are everything that makes that 0. Lambda 1 equals 1, to make the first one 0. Lambda 2 equals 2. And lambda 3 equals negative 1. That is our 3 eigenvalues for this matrix. So now, the next step is figure out what the eigenvectors are that are associated with it. So let's take this one as an example. We're going to find the eigenvectors that are associated with that eigenvalue. So the way we did that was we were looking for A minus lambda times the identity times X equals 0. Again, using our simplification from a couple of pages ago. So a minus lambda 2i, what's that equal to? A minus lambda 2i, when you multiply it out, you get, or you add it together, you get negative 1, 0, 0, negative 1, 0, 0, and 0, negative 1, negative 3, times x, times our vector x, equals 0. So again, now we have a linear equations. We know how to solve this. Put it into our augmented matrix and start row reducing. So when we row reduce this, I'm going to take 3 row 2 minus row 3 is the new row 3. I get negative 1, negative 1, 0, 0, 0, 0, negative 1, 0. And I'm going to get a row of zeros. And now I'm just going to multiply it out so that I get ones. So just multiplying a couple of rows by 0 or by negative 1. There. Now I have a leading entry there and a leading entry there. My x2 is my free variable. So if we write these out, we get x1 plus x2 equals 0. x2 was my free variable, so I just write it like that. x3 equals 0. Rewrite these just a little bit. x1 equals negative x2, x2 equals x2, and x3 equals 0. So now I can get my eigenvectors, being that x is equal to x2, my variable, or my free variable, times negative 1, 1, 0, though that is my eigenvectors that correspond to lambda 2 equals 2. So again, finding the eigenvalues and eigenvectors. First you get the eigenvalues by using the determinant equals 0. Gives you an equation. Once you have that solved out and figure out all the possible values where the determinant is equal to 0, take each of them in turn and solve the eigenvectors. What about lambda 1 and lambda 3? Well, I'll leave those as an exercise. So again, practice a little bit using lambda 1 equals 1 and lambda 3 equals negative 1. Use this technique again to get your eigenvectors. So again, the definition, if you're given a particular eigenvalue of a matrix, the eigenspace corresponding to that eigenvalue is the set of all solutions to that equation. This is called an eigenspace. We talked about eigenvectors. The eigenspace is the subspace that solves this equation. And this is really just the null space that we've been playing with all along. So for that previous example, my eigenspace, previous example, the eigenspace corresponding to lambda 2 equals 2 is the set of all vectors x2 times negative 1, 1, 0, such that x2 is scalar. Also equal to the span of my vector negative 1, 1, 0, using some of the other terminology and concepts that we saw earlier. So that is called an eigenspace. And what you have is that the set of eigenvectors is actually always an eigenspace, and that eigenspace is your set of, is your null space for the equation that you build. So now let's look at another example. So if we're given this matrix A, and I'm giving you the eigenvalue, we're going to find a basis for the corresponding eigenspace. So in this case, I'm again giving you an eigenvalue to make this a little bit simpler, but it's a good exercise to go through with this matrix, figure out what the eigenvalues are. So that's an exercise on your own. Just take that matrix, figure out what all the eigenvalues are for this matrix. Okay. But I'm telling you, one of the eigenvalues is lambda equals 4. So we're going to find the basis for the corresponding eigenspace. So again, finding the corresponding eigenspace, we have to find the solution to A minus 4 times I, the identity matrix, times X equals 0. So what's A minus 4I? Well, that's you subtract the matrix with 4 all along the diagonal from our matrix A. We get 2, 2, 2, 1, 1, 1, and 3, 3, 3 times our matrix X equals 0. Okay, so now we have the equation. We have to solve it out. So augment it. 3, 0, 0, 0. And we can do a couple at the same time here. So row 1 minus row 2 is the new row 2. You can see this one's pretty easy. Row 1 minus row 3 is the new row 3. We get 2, 1, 3, 0. And everything else turns into zeros. Which then just do one last step to put a leading 1. We get 1, 1 half, 3 over 2, 0. And the rest are zeros. So now we only have one leading entry, so we have 2 free variables. What does that mean for us? Well, we write down the equations. So if I write down the equations for that matrix, I get x1 plus 1 half x2 plus 3 over 2 x3 equals 0. x2 is a free variable, x3 is a free variable. That gives us our equations. x1 is equal to negative 1 half x2 minus 3 over 2 x3, and x2 and x3 are free variables. So what is the space? The space, this is the null space, so you take this and put it into vector form. x1, x2, and x3 is equal to, take all of your free variables, x2 times something. We have no constants again here, so we just have our free variables. Then put the equations in here. x1 gives us negative 1 half, 1, 0, negative 3 over 2, 0, and 1. That is the equation for our eigenspace that corresponds to our eigenvalue, lambda equals 4. We were looking for a basis, so the basis is equal to the 2 vectors, negative 1 half, 1, 0, and negative 3 over 2, 0, 1. That's the basis. So again, we took an eigenvalue, we found the eigenspace corresponding to it by finding the null space of A minus lambda I. That null space is called the eigenspace, and then we can get a basis. So any vector that you can build this way is going to be in that eigenspace. Try it out yourself. Stick a value for x2, stick a value for x3, combine these things, you're going to get a vector. Multiply that by your original matrix, and you'll find that your original matrix A times that vector is always equal to 4 times the vector you started with. That means it is in your eigenspace corresponding to the eigenvector lambda equals 4. This is an example that we haven't seen the other examples where you have your eigenspace with multiple vectors in the basis. We're going to be talking about things like this, how many vectors are in the basis for your eigenspace over the next couple of lectures. So finally, to wrap up, remember when we were talking about transformations, and we said that a linear transformation is really just a matrix multiplication in disguise. So for any linear transformation, you have a matrix that we called the standard matrix, or the associated matrix of that transformation, where that equation held. So a linear transformation was just a matrix multiplication. Similarly, when we talk about transformations, we will often talk about the eigenvalues, eigenvectors, and eigenspaces of a transformation, and we're really just talking about the eigenvectors, eigenspaces, and eigenvectors, eigenvalues, and eigenspaces of its associated standard matrix. So if you have a linear transformation and you're asked to find its eigenvectors, spaces, or values, just take the standard matrix for it and figure it out with that. And finally, here are some suggested practice problems for 1.